Okay, you know about the atomic numbers. That means in the periodic table, we have elements, and this is a characteristic feature about the atomic numbers, right? So all the properties of these elements depend on these atomic numbers. They are function of this, okay? This you know already, right? So you can see here, there are several types of elements. I think this is very basic things that I don't need to explain, but just for your refreshing your knowledge, we have metals, right? So the metals are in this color, you can see clearly. And then we have transition metals here, okay? The metals are here. And we have transition metals, and also, of course, there are other metals in this section as well. And we have transition metals in this group here. And there are a subgroup called inner transition as well. These are also metals. For example, you can see these very kind of, we call them lanthanides and actinides, right, here. And we have another term for that. We call them rare earth elements for these lanthanides, okay? Only for the lanthanides we call rare earth elements as well, right? And then we have non-metals, you know already about the non-metals. And some gases are there, right? They are not metals. And also within these non-metals, you have this particular group. What is this? Rare gases, right? Rare gases or inert gases. And also we have metalloids. So metalloids means partial metals, like they are not clearly metals, but they are not also non-metals, right? Therefore, we call them metalloids. So these are the broad category of elements that we have in the periodic table. But of course, there are other categorizations as well, right? And also for the geochemistry, we use a separate type of category of categorization of elements that I will take later on, right? This is just the chemical classification that is used in ordinary chemistry. Okay, right. So here we consider the geochemical classification of elements, right? This is a little bit deviated classification from the normal chemical classification or the chemistry classification, because we categorize them into their properties with respect to our earth materials. Okay, so this classification was first discovered by Goldsmith, right? So therefore we call it Goldsmith's classification of elements, right? There we have categorization as lithophile elements, chalcophile elements, and siderophile elements, right? These are the main three categories. Lithophile elements means the rock-loving elements, right? Litho means rock, right? These elements, these lithophile elements, such as oxygen and mainly oxide forms, right? And you can see this color, lithophile elements. For lithophile elements, this red color, right? In this periodic table, you can see them colored in red. They are lithophile elements. That means they are favoring the rocks, favoring rocks. That means in rocks you can find them easily, right? They are concentrated in rocks, because in rocks, you know, minerals are there. So minerals contain these elements. That means as a building block of minerals, these elements are found in rocks. Actually, these minerals we call rock forming minerals, right? these minerals called rock forming minerals because they contribute to form rocks, right? Some other minerals, because you know already about the mineral groups, right? Classification of minerals. We have several mineral groups. Only out of those, some minerals only contribute to form rocks. That's why we call them rock forming minerals, especially silicates. Okay. So these lithophile elements are contained in these minerals. That means they are found in rocks. That's why they are called lithophile elements. And then we have chalcophile elements. Chalcophile elements you can see here in this shaded type light orange like hatched mark in the periodic table. You can see copper, zinc like elements. They are chalcophile. Mainly these chalcophiles are concentrated in sulfides, in sulfide minerals. We know that we don't consider sulfides as rock forming minerals. Sulfide is also a mineral, but we don't consider them as rock forming minerals. Okay. So in the sulfides, you can find these chalcophile elements, right? To form sulfides, you need basically these chalcophile elements. For example, zinc, if you take as one example, zinc sulfide, right? What is zinc sulfide? Sphalerite, the mineral sphalerite, right? Like that, we have lead sulfide. What is lead sulfide? Galena. Okay, so they are not rock forming minerals, but they are economic minerals, one of the economic minerals. But since they prefer they are found in the form of sulfide, we call chalcophile elements because they have attraction to sulfides. And the other group is siderophile elements. Here you can see this color, this orange color or light pink color. Here in the periodic table, you have that. Okay, so they have kind of metallic forms, right? They are metallic, siderophile. They are almost like metals, like iron, cobalt, nickel, molybdenum, tungsten, like, right? All these elements they call siderophile because they prefer to be in metallic form. They prefer to be formed in metallic form. That's why we take them as siderophile. Okay, and then we have another group which is a minor group which we call atmophile. Actually, atmophile means they are mostly attracted to the atmosphere or the gaseous form, right? So here you can see them, carbon, nitrogen, and hydrogen in addition. We call them atmophile because they are much attracted to the atmosphere or gaseous form. So these are the geochemical classification of the elements. But in addition to these, we have another geochemical group which is also included in this classification, especially in terms of chalcophile and siderophile groups. They belong. For example, we have platinum group elements, platinum, palladium. Of course, they are metals, but they belong to a special type of properties. For example, so you see here iridium, platinum, palladium, rhodium, right? These elements, right? You can see both colors. The pink color plus the hatched pattern, right? These two, right? Because they are special. Okay, so they belong to platinum group elements. So we call them platinum group elements, right? Because they have a special type of behavior out of these two siderophile and chalcophile groups, some special properties. So therefore, we can take them as platinum group elements as well, right? PGEs, we call them PGEs. And gold also behave similarly to these platinum group elements, but since gold is a siderophile, clearly siderophile, it's separately considered. Okay, so these are the main geochemical classification of elements, and we frequently use them in solid rock geochemistry, hard rock geochemistry, when considering different geological processes. Okay, their behavior is very critical in geological processes. So we consider them separately, therefore. Okay, so these are the main categories. But out of these categories, we have this normal RE group, rare earth elements. Okay, RE rare earth elements, that is also important for us because in geochemistry we use their properties to discriminate different geological processes. Okay, different geochemical processes or geological processes, we use these different categories of elements. So this is a kind of a very basic classification of elements, because we might be using them in the future in our lectures. Okay, so isotopes. What are the isotopes? The definition of isotopes, as you know already. What is the definition of isotopes? Atoms of the same element. Okay, atoms of the same element, but with different mass numbers. Okay, they have a different mass number, but the same element. Okay, so that's what we term isotopes. So we have same element but with different mass numbers, so we can call them isotopes of a particular element. So this is how we name the mass number and atomic number. So if you have different mass numbers, that means we have different isotopes. Okay, so that is the very basic definition of isotopes. I think this you must have covered in your GSQ, the first year chemistry, or even A-level chemistry. So the notation normally when we call them, you can just simply call them carbon 12. For example, in this case, the mass number is 12. Carbon has isotopes 12, 13. So therefore, you can just simply say the mass number with the element name, right, as the notation. So you can just call carbon 12 or carbon 13 like that, right, to name the isotope. But when you write it chemically, this is the chemical notation, right? You have to show that this is correctly the atomic number and the mass number. Okay, so if we consider an atom, you know, we have nucleus, there is nucleus and electrons rotating around the nucleus, and neutrons are there inside the nucleus, right? So this is how the protons and neutrons are there, making a stable atom. Okay, so in the nucleus, what you have is neutrons and protons, right? Neutrons are not having any charge, protons are having plus, and electrons are having negative charge. So this is the basic structure of an atom. So for example, if you take the carbon, you have 6 neutrons, 6 protons, and 6 electrons. This is carbon 12. So what happens if the carbon produces another isotope? This neutron number will be changing. Okay, neutron number will be changing, but you don't see any change in proton number. Okay, if you change the proton number, means you are changing the element, right? So that is a characteristic feature of the element. And in carbon-14, as I said, what happens is you have additional 2 neutrons there, right? If the carbon-14 is considered as the isotope, there are 2 extra neutrons available. 2 extra neutrons available. So this is how isotopes are showing difference in their chemistry if you consider its pure atomic form. Okay. I think this is very basic thing. You can easily understand this. Right. So we have different types of neutrons, right? 3 neutrons here and 4 neutrons here. So that for lithium, for example, they make lithium-7 isotope, right? So these are very, very basic things. You can see no change in the electron configuration and also no change in the proton configuration in the nucleus. Only difference is the neutrons. So again, the same thing. You have this difference. Okay, so we have chlorine. Again, chlorine 37. It is an isotope. Mass is 37. Mass is 37. Atomic number is 17 for chlorine. And we have number of protons 17 and electrons 17 and neutrons 20. Right? This is how it composed up to 37 mass number. Mass number is always the neutron number plus the proton number. Okay, 37. We have some other concept as well. I think I don't know whether Peterwell has taught you this at the very beginning, but just you can consider this the relative atomic mass, the concept of relative atomic mass. But I think you know it through the chemistry as well. Relative atomic mass is given in atomic mass units, right? You know that. AMUs, right? Remember AMUs in your A-level chemistry, right? That is the 1 AMU means 1/12 of the mass of the carbon-12 atom, right? 1/12 of the mass of C12 atom, right? So if you consider one proton is equal to this much of AMUs. 1 neutron is equal to this much of AMUs, okay? And 1 electron is equal to this much of AMUs. So you can clearly see the difference in masses, right? The lightest is the electron. You can clearly see that. Okay, so this is carbon-12. This is carbon-12. And for carbon-12, you have 6 neutrons, 6 protons, and 6 electrons. Okay, so the mass of it, if you take the 1/12 of that mass, 1/12 of this mass, you can term it as the AMU, 1 AMU. Okay, 1 AMU will be equal to 1/12 of this carbon atomic mass, right? So this is another basic concept, right? So as I mentioned before, naming the isotopes can be given like this. Okay. For example, carbon-12, carbon-14, uranium-235, like that, right? There are so many types of isotopes. Any of them can be named like this, right? You can put the mass number there, okay? You can put the mass number. I think you can remember. We have Yeah, different isotopes. So lithium 7, for example, you put the mass number there, right? This is the mass number. Okay. So this is how we name the isotopes. Okay. Right. So there are so many isotopes. You can find them in in textbooks. I will give you 2 textbooks to follow, because this is very important, because there are so many examples in those textbooks that you have to read and comprehend and absorb. Otherwise, it's very hard for capturing this radiogenic isotope part, right? 2 books are there in the science library. You can find them. Actually, 3 books are there now. There is not a new book also. I will give you just for, if you can note, you can just note down the titles. That is Radiogenic Isotope Geology by Gunter Faure. Gunter Faure, Faure, the author name, right? Radiogenic Isotope Geology. And there is another isotope geology. Sorry, the book that I mentioned now is Isotope Geology, just Isotope Geology. Okay, by Gunter Faure. There is another book that is Radiogenic Isotope Geology. That is by Alan Dickens. Alan Dickens. Okay, Alan Dickens. That is another textbook, very famous textbook. Alan Dickens. And the third one is the newest one, the most recent one. That is Isotope Geology by Francis Albarade. Francis Albarade. Okay, this is a big book, but it is already purchased in the science library, so you can refer it. Maybe it's only found in the reference section. You might not be able to borrow them. Okay, right, but you can refer that within the library, or you can get copies of not all the book, but the important pages, chapters. Okay, so we have another concept, that is average atomic mass. Average atomic mass. What is the average atomic mass? That is the weighted average of all isotopes, right? Weighted average of all the isotopes. Normally, we put it into 2 decimal places, right? Weighted average of all isotopes means, one isotope can, one element can have different isotopes, right? For example, carbon 13, 14, like that. You can have several isotopes, and these isotopes are abundant in the Can you hear me?
Yes.
Okay. What about the shared screen? No? Can you see the screen?
Yeah.
Okay. Right. So average atomic mass. Average atomic mass means the weighted average of all the isotopes. Okay. Weighted average of all the isotopes. We round it into 2 decimal places, because in the nature we have different abundances of these isotopes. Okay, all the isotopes are not present in equal amounts. That's the idea behind it. Okay, all the isotopes are not found in same abundance. Okay, we call them the abundance of the isotopes. So this percentage mark means the abundance of that isotope, right? So the mass of the isotope multiplied by abundance of it gives the relative amount of isotope in that species, right? That is what you call the weighted average. Okay, this is the weighted average. So if you have one isotope, this is the weighted average of that. And if you have another isotope of that particular element, that is the weighted average of that mass into the abundance of that. Okay, how much it is available. That means if you take 100 molecules of that element, this amount will be its abundance. For example, if you have X abundance, means X percentage of an abundance of an A element, means if you take 100 atoms of that element, you will find X numbers, right? X amount in that particular isotope. That is the abundance. So average atomic mass is given by the weighted average of all the isotopes. So we considered 100 atoms, so therefore we have to divide it by 100, right? So if you had more, you can put more there, right? So everything will be summed up to 100, so therefore you can divide it by 100. Okay, so if you have more atoms, more isotopes, then you can consider their abundances and then calculate the average atomic mass. So for example, if you consider average atomic mass of oxygen, okay, average atomic mass of oxygen. So if you want to take that calculated, right? So you are given abundances of O16, because you know O16, O17, and O18 are the availabilities of isotopes of oxygen, right? So oxygen O16, you have O16, oxygen 16, 99.76, and oxygen 17, 0.04, and oxygen 18, you have 0.2%, right? These are the abundances in the nature, right? Remember, this is in the nature, right? In the nature, the natural environment, right? So average atomic mass, so you have to weight them accordingly, right? Weighted mass you have to consider. So how much? Oxygen 16, sorry, the mass is 16, and abundance is 99.76. And for 17, you have 0.04 abundance, and for 18, you have 0.2 abundance, and you divide it by 100. Okay, this will give you the average atomic mass of oxygen, and it is given in AUMs, right? Remember, this is given in AUMs. So this is the average atomic mass. Similarly, you can find another thing, that is from chlorine. Chlorine, you have you are given it like in a different way. So find average atomic mass of chlorine if approximately 8 of every 10 atoms are chlorine 35 and the rest are chlorine 37. So we have two isotopes of chlorine 35 and 37, and they give us as a ratio, right? Every 10 atoms, if you count every 10 atoms of chlorine in the nature, you will find 8 of them as 35, right? 2 of them as 37. So this is not a percentage, but you are given a ratio only, but doesn't matter. You can apply that also to the AMU or the average atomic mass equation. So you can directly put these numbers, or otherwise you can just calculate the percentage and put there, right? Whatever. But it's okay, you can put the ratio, because whatever the percentage is also a ratio. So you can directly put it 8 here, because we are counting 10 atoms, and you can put 2 here and divide it by 10 instead, right? We did not consider 100, but we consider 10 only. Therefore, you divide it by 10, right? That is also fine, right? This is also fine. So this is how you can do you can do calculation. Okay, so Try to find out what is the number. Okay, did you find out the number? So this is the number that you are getting, right? 35.4, right? That is the average atomic mass of chlorine. So average atomic mass. So this is the average atomic mass. So you have to know that the mass of this atom, right, should be in average this much, because actually if you are considering chlorine means it's a mixture, right? It's just a mixture, not like other elements which are not available in isotopic forms, right? In isotopic forms, you have different masses. That's the basic idea. So you can't say exactly the mass of chlorine is this, like that, because you have different masses of chlorine atoms. So what you the best way to present it is to make the average atomic mass. For that, you have to take the abundances of isotopes of these elements and then give a mass. Otherwise, the mass that you are referring might be not correct. For example, in A-level chemistry, you might remember for chlorine, you took the mass as 35, I think, right? Because that is the most abundant isotope, right? But actually it is not 35, but you can see its average mass is 35.4 because we have to consider all the isotopes, right? So that's why we have to be cautious about isotopic abundances. Okay, do you have any questions? We are just still passing the very preliminary things which should have been taught at the A levels or in your first year chemistry, right? I hope everyone has done chemistry at the first year in the university, or at least at the A levels, out of you. Okay. Right. So we'll see a graphical representation of this chlorine. We saw the highest abundance was given by 35 chlorine. Okay, 35. And the least abundance was given by 37. You remember 8 out of 10 is 35. 2 out of 10 was 37, right? So if you take a mass spectrum, this is what you call a mass spectrum, right? We can take them, we can produce them using a mass spectrometer, an equipment called mass spectrometer. If you put all these atoms into the mass spectrometer, then it will provide you a mass spectrum, which will give you a picture like this. Okay, you will get a picture like this in a mass spectrometer. So these peaks, we call them peaks. Okay. These peaks are important. These are characteristic peaks because if you have an unknown mixture of a sample, right? If you have an unknown sample, if you want to recognize what is included there, you can have a mass spectrum there and find out, right? So you can refer these mass numbers because these mass numbers are characteristic. They cannot be sulfur, or they cannot be oxygen or silicon. They cannot be. This should be chlorine. Okay, so like that, you can find the unknowns in a sample by looking at a mass spectrum. You can resolve their masses into peaks, right? We call them resolving, right? We are resolving the mixture into components. Okay, this is how we get the peaks. Okay, so this is the mass spectrum, and this chlorine, even though we take Cl2, right, chlorine, which contains a mixture of two isotopes, okay, two isotopes, and you have abundances like this, right? So these are resolved into two peaks. These are the two peaks given by the mass spectrometer, right? We can determine what is in there. So if you get some other mass peaks like this, right? For other numbers, we don't know other numbers, say 100 or so, right? Then the mass characteristic for 100 should be there, included in that particular mixture. So likewise, you should be able to figure out what are the other other elements or other isotopes available in that mixture, right? So the mass spectrometer is a very important and useful equipment, right? To get the mass spectrum, right? For a mass spectrum of an element or a mixture, whatever. Okay, these are chlorine 35 and 37. So with the abundances we calculated before, like that, right? So what is a mass spectrometer? As I said, it's an equipment. It's an equipment which counts masses, using some mechanism, right? Spectrometer, spectrophotometer or spectrophotometer. These are two things, right? It's a resolving, mass resolving kind of a meter, right? Photometer means in terms of a signal, it can give you light signal or something like that. Or otherwise, if it is just a spectrometer, then it can be given as an electronic signal, right? These signals can be counted somehow, right? These signals should be counted to see how many atoms are there. So that is the basic principle in a mass spectrometer or a spectrophotometer. So first, what you need there is an electron beam, right? So this electron beam should be there, and this electron beam will produce some kind of a gas, some kind of a gaseous material from the sample, because we have a sample here, and when this sample is bombarded with an electron beam, actually now for a mass spectrometer, no electron beams are used. We have to use an ion beam instead. Ion beams. You will learn these things when we learn about the instruments, right? Under the analytical techniques, you may have learned this already, but we can learn further later, okay? Ion beams means like cesium, oxygen, like ions. They are not the elements, but ions are bombarded. It's possible, right? Then somehow it is made into a gaseous form, the materials, and in these materials, as you know, they contains different masses, right? So that will be put into a magnetic field. So this is the basic principle. You put all these mixture into a magnetic field, and with the magnetic field, there is an acceleration, right? Here you have an acceleration, right? So they will have different speeds. That means they will, the different ions will be separated into different segments, right? That means based on the speed, you will see different masses will hit in different places. We call this as the component of detector, all this section, right? All this section we call as the detector, right? So all these things will hit there and separated. So we call resolving, mass resolving. That means you are separating out the mass, You are separating out the mass means you are separating out the isotopes, right? So here you have one isotope, here you have another isotopes, and here you have another isotopes. Likewise, you can count the number of atoms that are reaching this detector. 1, 2, 3, 4, like that. There will be so many atoms hitting there at a given time, right? Because this is happening continuously, right? So from this cloud at a given time frame, the volume of this gaseous form will be going into this magnetic field and accelerated, and because of that, at different places or at different time intervals at different places, you will hit these ions. So based on this ion path, there are detectors, separate collectors in the detector, right? Like cups, we call Faraday cups. These are called Faraday cups. The name of that is Faraday cup, right? Why we call Faraday cup means it's coming through the magnetic field. So, Faraday has a connection with the magnetic field. So these detectors, these separate cups, that means they collect these atoms into this, right? Actually, from there on only some electronic signal will pass. Electronic or a photo signal or light signal will pass based on the number of counts there, right? In terms of electron volts. Okay. So actually there is a very complex electronic circuit board connected to this, and that is connected with the computer. Okay. So this is connected with the computer, and this electron volt will be converted into some signals. Some signals that, like you saw in the previous slide, mass spectrum, right? You saw this one? Yeah. So these electronic signals will be converted into this type of a graphical signal by softwares, right? In the computer, you have softwares. So those softwares will convert them into a graphical form so that the end user here can understand that. Okay, so this is the basic principle behind a mass spectrometer, where we use to find out the isotopic ratio, isotopic species. We call them species, right? Different forms of a given element. You can call them chemical species. So this is a basic principle behind a mass spectrometer, but there are so many complex types of mass spectrometers, right? So actually, the first mass spectrometer was produced in 1919, okay, by a person called Aston. He has received the Nobel Prize for this accomplishment in 1922. Okay, in 1922 for this invention. So what is happening is the gas sample enters here at the first place, and actually there are different mechanisms, right? This is one of those mechanisms where a filament is used. In this case, a filament is used to ionize the sample or gas, right? In the previous case, we used an electron beam, right? Or ion beam. Remember, electron beam or ion beam can be put there, and the sample is lying here on the filament in this case, right? So drops of samples, right? It's a drops of sample, and once this is hit, what happens is everything is atomized, right? Here everything is atomized into the gaseous form. It converts into the gaseous form, right? Here stream of gases here. This is the place that we are looking at in the instrument, in the real instrument. This is just a schematic form. Okay, so all these are atomized with the help of this ion beam or gas ion beam or electron beam. Okay, this is the sample location. We have to load the sample into here, right? Then only you can switch on the gas beam or electron beam. Then it will be atomized. It will be atomized and of course heated also because of this filament. Ionization is taking place, and then it goes in this direction to a window or a slit, because from there onwards only it will get accelerated, right? Until that place there is no acceleration. So acceleration is provided from there onwards by this slit, right? So these are very tiny hole-like thing. Okay, so everything will be atomized, and atomized particles will hit this slit and penetrate through that and get accelerated. And once accelerated, it goes through the magnetic field. Here you have the magnet, huge, I mean, very strong magnet field, right? These are the magnet field. So they are passing through a magnetic field. So once they are passing through a magnetic field means they will separate into different isotopes, right? Different isotopes means different masses, right? Depending on the mass, they can be separated. That means, in other words, they will be separated out into the isotopes. The mixture will be separated out into the isotopes, right? Here the mixture is there, so they will be separated out in this magnetic field. So magnetic field is very important. Otherwise, even though you accelerate it, you cannot separate them into different species, right? So then they hit the detector here, right? So you have the detector here, and the cups that I mentioned, Faraday cups, they will be placed somewhere here in different places. Okay. The heavier ones divert more, the lighter ones go somewhere there, like that, right? Depending on the mass. So this is the phenomena of mass spectrometry. So we use them to determine the isotopic masses, right? And also abundances can be calculated in unknown samples. You can count them, how many 35 atoms were there, how many 37 atoms were there, like that, right? For example. So we can interpret the mass spectra with the computer. I said you can get a graphical form of these kind of curves or peaks. Then we can interpret them, and also we can find out the average atomic weights of these masses, right? These atoms. So this will finally give you an idea about the natural variation of isotopic abundances in the sample, right? In our sample, which might be an unknown sample, right? So we can have a rock sample which can be dissolved and put in as a liquid form here, some drops, and then you can find what are the isotopes available there. Actually, this isotopic abundance tracing is very important for us to understand geological processes, many geological processes, because you will find out different isotopes, and their behaviors can be interpreted in terms of geological processes, because some geological processes show some characteristic phenomena regarding the behavior of these isotopes. And also some isotopes we can use effectively to do age dating, right? So age dating is one thing, and understanding geochemical processes is another thing, right? Whether the sample is derived from mantle, whether it is coming from the crust, or whether it is coming from mixing of crust and mantle, or whether it is highly depleted, and so how it becomes that depleted, whether it is mid-ocean rich basalt, or whether it is island arc basalt, or whether it is coming from accretionary complex, like that, right? So many geological environments can be traced after by analysis of these isotopic signatures. Those are the geochemical tracing, right? We can use the isotopes as a tracer, 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 as a geochemical tracer. That means to understand the interior process, which is unknown but happened so many millions of years ago. That is one major advantage. The other one is to do the age dating, to determine the absolute age, exact age of that particular rock or a mineral, right? All the age dating has been done using these isotopes. Even the age of the Earth or even the age of the planetary system was determined using this isotopic system. So radiogenic isotopes are very, very important because of this case, right? For stable isotopes, there are separate mass spectrometers, and for radiogenic isotopes, there are separate mass spectrometers. Remember that. But the concept is same. This is the concept. For radiogenic isotopes, you have separate mass spectrometers because their mechanics and their optical features are different. Okay, so I think we have come to the 1 hour time. Since you also have some other lectures, we will stop here for today, and we will continue from the next week. And if you have any question, anytime, you can interrupt me during the lecture also and ask, right? This is very important because this is not an easy lesson, right? I mean, unless you grab the principles, otherwise it will be very easy, right? Okay, so I will stop here for today, and we will meet next week. Okay, right. So please make the attendance sheet submitted to the office. That is very, very important.